All right. So when we left off, feels like forever ago for some reason for me. But when we left off, we were getting into pipeline and this multi-processor architecture. And so we had kind of gone through and we talked about this concept of a pipe, right? How do you make it more efficient? We said, well, you could either make the pipe bigger, right, to get more stuff through it, okay? Or you can make it faster by maybe getting a more like powerful pump, right? And the idea was that we were trying to increase this concept of throughput, right? In the case of a pipe, maybe the amount of oil flowing through it or something like that. And then we basically kind of came onto this idea that, well, maybe we could just add more pipes, right? We've got all the parts to make new pipes. We've got the pumps, you know, to push them through. We don't need to go and redesign a part. We just order more of those parts, okay? And so that's the general idea of pipelining, is that we're just gonna do multiple things at the same time. Okay, and we started to talk about what that looks like from an architecture perspective, right? And we talked about different types of parallelism. So there is ILP, which is really what we focus on when we talk about processor architecture. At least it's, I don't know, I don't want to say it's the more interesting. It's definitely the more intricate version of parallelism. But with ILP, instruction level parallelism, we'll hear keywords like pipelining, which we've talked about, in the superscalar architectures, okay? And we'll break those down in a second, just as a reminder. And the idea behind ILP is that we're actually doing some kind of parallel operations at the instruction level. We can actually potentially break down a single instruction and execute parts of that instruction in parallel, okay? Versus when I get to this processor level parallelism, this is a much higher level coarse grain parallelism. This is taking perhaps two different programs and running them at the same time, which you would expect is a lot easier than instruction level parallelism, right? So we're talking about actually having multiple processors here, multiple computers and whatnot. Okay, so we talked about pipelining. Typically, we can break down a lot of those pieces that we saw in that basic microarchitecture, that IJVM. We can break them down and do those in parallel. Okay, so the idea is that we're pumping multiple instructions through our pipeline at the same time. So here we had at time one, we start instruction one, and you can see at time one, instruction one is being fetched, and then at time two, instruction one is being decoded. At time three, instruction one is fetching the operands, and then at time four, instruction one is being executed. And then at time five, whatever the results of that instruction are being written back to the operand stack in the case of IJVM, or if we're talking something like MIPS where we have registers, it's writing it back to one of those destination result registers. Okay, so if you just look at it from a single instruction, it's going to be pretty much kind of the same flow. But the key with pipelining is that, hey, I've already, you know, by time one, I'm done fetching the instruction for instruction one. I'm done, right? So why just let that instruction fetch hardware go to waste, just sitting there doing nothing, right? So in that case, we say, all right, well, let's actually start reusing that hardware. Let's go and fetch instruction two. So the time you're fully cranking, you can see that this is like an assembly line where every single part of the assembly line is working on a different instruction. Just like in an assembly line of a factory, every single point of that assembly line is working on a different car. And every station is doing the same thing. Once they're done with their part, they pass it on to the next station, and then that person will do their particular part. So same thing, as you see here, this is really generic, but this is pretty typical where we would start for pipelining with these 5 stations, where, you know, every these stations are just doing this one task. Once they fetch the operands here, they pass it on, right? And so on and so forth. Okay, and the idea is that we're really going for throughput here. Okay, and we went on to the next slide and basically showed how we can have a processor that's actually running at a much lower frequency, right? So here we had a 200 megahertz processor because we had a 5 nanosecond period. Here we had a 15 nanosecond period, which essentially equates to 66 megahertz. All right, and the idea was that, hey, this one is cranking along at a much faster frequency, but it's non-pipeline. So you put one instruction in and it goes out. And as soon as that instruction's done, then the next instruction begins, right? Whereas our pipeline computer looks like the slide we were just on, right? Where we have multiple things going on at the same time. This would be a 5-stage pipeline that I'm showing right here. The example that we talked through in class was actually a 6-stage. So don't worry about the stages, right? But just kind of take into account that, hey, the designers were able to come up with 6 unique stages. And even though this processor was running at literally 1/3 of the speed, you can see it essentially has twice the computing power. If you want to kind of look at how many instructions are able to be processed in the same amount of time. And that's because we have that 6-stage pipeline. So after the first 6 cycles or whatever, we're getting one instruction completed every cycle. So then we kind of got into this concept of dual pipelines and having multiple units here in parallel. And this is where we come up with the idea of a superscalar architecture. Okay, and a superscalar architecture is one that really, the main thing about superscalar is that it's pipelined. Okay, so we have these multiple stages, but we also can have multiple execution units. So you can see here that we have 2 ALUs, 2 a load and a store and a floating point unit. Okay, but the idea is that we can execute 2 instructions at the same time. So you tend to get with superscalar, you can get something like this where you're actually dispatching 2 instructions at a time, right? In the previous slide where I showed the pipelining, there was only ever 1 instruction that was being dispatched at any given time, right? But with superscalar, you can start to do 2 or more depending on the actual setup that you have. Okay, so from there we went on, and this is kind of where we left off to talk about hyperthreading. Okay, and hyperthreading is Intel's kind of buzzword, keyword technology. And the concept that we saw there was that more and more processors will have multiple cores. Okay, so like in this case, we actually see a 4-core processor. Okay, so what that means is it literally has 4 of these data paths that we've just been looking at. Okay, so 4 separate unique data paths, 4 separate unique processors. It's just like you typically think of, hey, I put a processor down in my motherboard, right? It's just that modern processors have like 4 of those smashed into one physical package. Okay, but where hyperthreading makes a difference is that it's able to, and this is kind of at the hardware level, it's able to essentially take one of those cores and make the operating system think that it's actually 2 cores. Okay, so if you have 4 cores here, it's actually able to make the operating system think that you have 8 cores. Okay, and the operating system doesn't know, hey, this is actually just one data path, and maybe it's it's pipeline and superscalar and all this stuff, but the operating system thinks that it has 2. It gets like 2 for 1. So what that means is that you can kind of see this image down here, and we watched the video. But essentially what that gets us is the operating system, and instead of thinking it can schedule 4 things at once, it thinks it can schedule 8 things at once. And the hardware underneath basically takes care of all the details. Even though it's just, if it schedules 2 threads, 2 different programs to the same core, it's a really challenging task, but the hardware will basically figure out how to organize those tasks, how to break them down in such a way that they're basically happening at, nothing really happens at the same time. We talked about from the very beginning, things are just happening so quickly that it looks like it's at the same time. But for all practical purposes, right, we're interleaving these 2 threads through the same general hardware. Okay, so we watched a little video on that, and this is where we pick back up. Now I'm going to kind of go briefly through some of this data parallel stuff because I just kind of want to expose you to a few very basic ideas. So this is CUDA. Okay, so ECE, you guys are painfully familiar with this, right? CUDA. So the idea behind CUDA is you guys have these really awesome graphics cards, right? How many of you guys have an NVIDIA GPU and like maybe an aftermarket one? And even if you don't have that, you probably have some kind of like, you might even have in your laptop without knowing it, some kind of like NVIDIA graphics in there. But the idea is we have these amazing, expensive graphics cards in our computers, and they're good for nothing, right? All they can do is play games. What's that good for, right? I mean, hopefully I'm not joshing too much, you guys. But you know, all we can do with them is play games, which is great, and that's, I guarantee you, what you bought it for. But as people started to look at these graphics cards, they started thinking, hey, there's a lot of processing power here, right? If you recall a few chapters ago, remember when we were talking about teraflops and flops, and we said, hey, let's look at the Xbox One, Series X, and the PS5, and they give us these, like, it was like 10 or 12 teraflops, right? Floating point operations per second. And we looked at the processor and we said, there's no way the processor can do that. And we realized it was the graphics card that gives you that super high. Remember, anytime we're talking about per second, anything per second, we're getting at throughput. How many things can I do per some amount of time? So that's exactly flops, teraflops, or whatever. So the GPU, with GPUs, essentially what NVIDIA, you know, started to realize was, hey, we've got all this processing power. Instead of having one or a dual core or quad core processor, I literally have thousands of processing cores on a GPU. Now they're not general purpose, but if I can do some kind of instruction with it, I can massively parallelize it onto this, you know, group of 5,000 or 6,000 processors. So that's the idea behind GPUs, is essentially, let's make this fabric programmable in a somewhat general sense, okay? So if you want to do adds and multiplies and things like that, that's very much in the realm of the things that you can do with your GPU. So CUDA, all CUDA really is, it's a library, an API. It's a set of C++ functions, really, that allows you to access your NVIDIA GPU so that you can run somewhat arbitrary code on it, okay? Otherwise, right, the people who are making video games with Unity and things like that, you know, they're able to tap into that, but those are obviously using specialized APIs and drivers and things like that that aren't quite as generally programmable like something like CUDA would be. So processors like this, or let me say, I don't know if processor is the right word, but data parallel computing devices like this fall under the category of SIMD. Okay, so single instruction, multiple data. Okay, and the idea behind single instruction, multiple data processing engines is that I have a single instruction and I want to run it on a ton of data. Okay, the data is not necessarily like connected to one another. And so the idea would be, maybe be, as a simple example, right? Let's say that I had an array of like 10,000 items, right? I have another array of 10,000 items, right? And I essentially wanted to do something like this. For int I equals 0, I is less than 10,000, I plus plus. Okay. And, you know, I have some other, in this, you know, these have a bunch of data. Let's just say this one maybe empty. So basically C of I is equal to A of I plus B. Right. So as you can imagine, right, I mean, this is going to be just a loop that's going through and computing each one of those. And it's just, you know, it's literally just iterating through these three arrays, through the two arrays, and then saving the result in the third one. So that is very much, you know, C equals A plus B is very much something that could be parallelized, right? Because none of those operations are connected. You know, I could unroll this, and if I could toss each of those I equals 0, I equals 1, I equals 2, I equals 3, all the way up to 9,999, right? I could toss each of those to a different processor, and they could compute them just fine. So that's the idea behind CUDA, and I have all these cores, and so essentially, I want to assign, you can see all those little green boxes there, is I would assign I equals 0 to that top left one, right? And then maybe I equals 1 to the next one to the right of that, and so on and so forth. And so even though these cores are quite a bit slower than your CPU might be, right? Your CPU might be running at gigahertz versus your GPU is probably a few hundred megahertz. I think modern ones are getting up there into the low gigahertz, which is pretty fast. But these GPU cores are going to be slower than your CPU core for sure. Okay. But anyway, that's the idea behind data parallel computers. It's just that the graphics card, your GPU, is the most common one that you may already have in your own computer. So if you do have a NVIDIA GPU, then you could really speed up some code if it was in this form where you were basically running the same instruction on a ton of just different data. Okay. So this video, I'm actually not going to play it now, but it'll basically kind of show you. Let me just click on it, see if I. Yeah, it's probably will blue screen me. This is not, no, I don't think I really want to watch this. Let's just. Let's see. Oh, I can't stop my music, so you know. I can't stop my music, and my computer's starting to struggle, so I'm just gonna hope we can get out of this slide without a blue screen. There we go. All right, I think we made it. My machine blue screen the other day. I literally was just sitting in my office for like hours, and I come back and it was just like on the memory check screen. So you know, I want to push it. But anyway, that video, like all it really does is it just kind of shows you what graphics cards do, which a lot of you guys know at a high level, but it just kind of breaks out some of the terms that you'll typically hear. You don't need to watch it. You can if you want. Okay, so just a few key terms and a few things to think about. Multiprocessors. Okay, so multiprocessors is this concept that it is just what it sounds like, right? I have multiple CPUs connected in a system. Okay, and there's basically two ways that we typically see this done. Okay, one is that I have all these CPUs and they have this shared memory. Okay, so it's like the shared memory that is external to the CPU itself. And kind of the other configuration would be that each CPU has its own memory, okay? And then there's also a shared memory, okay? Now, maybe this is just connected over a local bus. If these are like actual different computers, like a physical computer here, a physical computer here, then this bus, you can think of it as like a network, right? Some sort. And the really hard part about all of this, keeping multiple CPUs like in kind of sync with one another, is this last statement. It's very challenging to keep local memories consistent with one another. Okay, and this is a concept called cache coherence. Okay, and in our last chapter, we'll talk a little bit about, well, the main thing we're going to talk about is memory and cache. And we'll talk about cache coherence a little bit. But as you can imagine, it's one thing if each of these CPUs is running, let's just imagine that instead of CPU, let's just call these cores, right? Because that's kind of, we'll give you a better picture of what we're talking about. Think of this whole box right here as a physical component you're going to put in your computer. I go out and buy an i7. Inside of it, there's going to be 4 different CPU cores, right? Each one of those is going to have its own cache. You'll hear things like L1, L2, L3 cache. You guys have probably seen those marketing numbers when you're looking at computers. Each one has their own kind of local memory, okay? A lot of times what you might get is you might have, each one has their own L1 and L2 cache, and then they have a shared L3 cache. And again, we'll talk about caches in the next chapter. But for now, just think of it from this perspective. So imagine these are 4 different cores, and each one of these cores is running a different program, okay? That's not such a big deal, right? Because the program really only maintains its own memory, right? If I'm running Spotify, it only needs to reach into the memory of the Spotify data. If I'm running PowerPoint on another core, it really only needs to access the PowerPoint data. But now imagine that I start to do some really interesting things and I say, well, hey, Spotify, itself is actually a multi-threaded program. More realistically, has anyone ever done like video editing or something like that? Once you start getting into like digital editing, video editing, image editing, that's where that type of software like Adobe is going to do a lot more things in parallel. And you can kind of imagine why, right? Because it's kind of like what we were talking about here. There tends to be a lot of single instruction, multiple data where it's like, hey, I just want to run this filter on this entire image of, 1 million pixels or something like that. So you tend to get more parallelism within the same program on those types of programs. But let's just imagine, right? You have, let's just say Spotify, right, is now spread out over 2 cores. Well, you could start to imagine that they're going to need to access the same data, right? Maybe one of those threads is actually playing the music, and one of those threads is drawing the display as you're clicking through kind of the main core, which is actually pretty realistic. That probably is true in terms of how the program is created. So you've got this core right here and this core right here, both connecting to the data. Now let's say that one of these cores modifies a piece of data that this other core who's also running Spotify needs to access, right? But I modified the data up here, and this core has no access to that data, has no clue that the data was changed, okay? So that's a very challenging problem, and that's this concept of cache coherence. And again, I don't want you to worry about how that problem is solved right now. I just want you to kind of know that that is a problem that we do have to consider. Okay, so we're about to transition back into kind of a little bit of pipelining, and we're gonna talk about how pipelining actually fits in with the IJVM microarchitecture. So we're gonna take this architecture that we've been looking at, and we're actually going to start breaking it down into pipelines and show you how we would actually update that microarchitecture to do so. So let's just take maybe just 1 or 2 minute break just to kind of context switch your mind, and then we'll pick back up here in just a minute.
Are we going to the luncheon? Oh, no. Yeah. Yeah. That's great. She's really that. That's very memorable. Yeah.
All right. Let's keep going here. All right. So getting back into this concept of pipeline, which I already kind of gave a brief overview, so we'll kind of blaze through these first few slides. But essentially what we're going to do is we are going to take that MIC2 architecture, which we left off with, and we're going to make some modifications to it to show you how we would actually pipeline that architecture. Okay, so just as a reminder, this was kind of this was the MIC2 architecture that we had. So remember, we started way back when with a single bus out here and it flowed into the H register. And then with the MIC2, we added that A bus all the way up and down. So now we have this A bus, we have the B bus, and we added this separate instruction fetch unit, right? So we said, if we have that separate instruction fetch unit, then essentially I don't have to do this thing where I am using the main ALU to do that PC equals PC plus 1 all the time, right? Now I just have the separate little incrementer, which will kind of offload that from the ALU, okay? So if we look at this, I'm gonna kind of zoom in down here to the left, right? We had this timing diagram, right? And we said, well, we've got these major stages where data is kind of flowing. And if we kind of think about it logically, we could break it down into 4 stages. Well, one of them was this delta W. Okay, so you can see delta W is when we're setting up the signals to drive the data path. Okay, and then the delta X was driving the H and the B bus. Now this was this timing diagram was from the MIC1. Okay, so if we would update that for the MIC2, it would say driving the A and the B bus. Okay, so basically driving those 2 buses and getting that data to the ALU. And then that delta Y was actually running those signals through the ALU and the shifter, right? So that's the delta Y. And then the delta Z, we'll zoom back out here. Okay, so again, delta W is just the control signals, getting that, decoded and all that. The delta X was essentially getting the signals out of these registers and then down to the inputs of the ALU, all right? So whatever the longest path is, which in this case, right, it's all the way up here, assuming this was like a physical picture of how things are actually organized. MDR really is the furthest away from the ALU. And then the delta Y is basically how long it takes for the signal to propagate through this ALU and the shifter, right? And the worst case scenario. And then the delta Z is essentially, all right, now that it's made it through the shifter, how long does it take for it to go all the way up to the furthest possible destination, which in this case, is the MARA up here. Okay. Now, this may or may not be how this physical hardware is arranged, but just for, kind of description purposes. Okay. So what we see is there's a few major components to this actual data path. Okay. Remember, the control signals was something else. But as far as the data path, we had that delta X, the delta Y, and the delta Z. Okay. So the idea behind the MIC3 is it's just a pipeline version of the MIC2. And we just take those 3 chunks, and all we do with pipelining is we just add latches in there. Okay, so just like flip-flops, if you want to think about it like that, a latch or a flip-flop, right? We're adding some kind of memory unit on those lines. Okay, now this just kind of shows it as an A latch or a B latch. But remember, these lines are like buses, right? I think these are 16-bit addresses or something like that, right? 8 or 16. And so these latches are going to be 8 or 16 flip-flops, depending on however big this these particular lines are. Okay, so just to make that clear. But conceptually, right? So what we see now, okay, is these latches allow us to operate in 3 distinct stages. Okay, so what we can do now, so remember the sequential circuits, how we had the next state and the current state, right? When you guys made those circuits in the project, that was the key. Once you kind of realize, okay, the output of the flip-flop, what do we say? The output of flip-flop, is that going to be the next or the current based on the project? That the next or the current. Let me ask you this. The output of the flip-flops, was it feeding back into the circuit to compute the next? Or was it, or was it connected to the outputs of the entire, like the lights and whatnot? Connected to both, really, right? So the idea is that that's the current, right? The output of the flip-flop is the current because we typically had something like this, right? Here is the flip-flop. And we had this Q output, and that would like connect to the light bulb, right? but it would also go back in, right, to some other, well, I don't know what happened there. Apparently found the gesture for erasing the last thing you did, if you squiggle. So as the idea, right, is this would be some circuit, right? So the output of the flip-flop, right, it would be connected directly to the light because that's the current state. But I would also use that current state and I would feed it back into some other circuitry to compute the next state, right? And then that next state would be what's the input to the flip-flop, okay? So if you think about it that way, right, the data that I have flowing out of these registers onto the A and the B bus, right, comes down and it latches into these A and B latches. Okay, so think about it like this. I have instruction 1 happening right there. Okay. And then I go to the next cycle. Okay, and basically my data for instruction 1 is in these latches, saved. Okay, so as soon as I start the next cycle, that data is no longer just being saved into the latch, okay, but instead it's actually now down here in my ALU, it's coming out of the latch, okay, which means I can now have instruction 2, right, the data coming down for that one. Okay, so I have instruction 2, the registers that I need, maybe it's a new add, they're coming down, they're flowing down into that A and B latch saying, let me in, let me in, let me in, okay? Meanwhile, the A and the B latch have the current, you know, well, I don't know if that makes sense to talk about it like that, but it has, you know, that first instruction and it is releasing that value into the ALU. And obviously that is flowing, right, to the C latch, okay? And at some point, right, whichever one is slower, and I mean, these are designed to be the same exact length of pipelines, but at some point, we get to the point where we have instruction 2 is sitting there knocking at the door of latch A and B saying, let me in, let me in. And then instruction 1 is knocking at the door of latch C and saying, let me in, let me in, let me in, right? So after that all happens, right, as you can imagine, we just go to the next. All right, so now instruction 1 is coming back and maybe being written into some other, you know, the write back register. And then instruction 2 right, it's flowing through the ALU and into the C latch. And then I have this third instruction, instruction 3, which is taking in 2 particular values, right? So now you can kind of see how with these latches, we're able to save just a small portion of the results, like the current result of this instruction, or at least the most relevant parts, right? In this first stage that has, you know, instruction 3 in it right now. Really all we want to know is, hey, what are the registers that we're about to feed into the ALU? What are the actual values? So we save those in A and B, okay? And then at the end of the second stage, we want to know, hey, what's the result of that ALU, right, that I'm about to write back into the register. And then you can see this third stage has a natural latch already built in because we're writing it back to one of these registers. Okay. All right, so what's the impact on my clock? I want to think about it like that, right? If we imagine that, okay, if we imagine that I had, you know, some amount of time in it, you know, what's the amount of time it takes in the worst case for data to flow, you know, out of the furthest input register down through the longest ALU path, the longest shifter path, up through, you know, and back to the furthest away register, right? I had some amount of time X, right? Maybe it was 5 nanoseconds, maybe it was 10, maybe it was 1, who knows, right? But let's just call it X. So the general impact, right, is that very roughly our clock cycle is going to be divided by 3 because we basically converted this long single stage data path into 3 smaller data paths that we can execute in parallel. okay? So very roughly, right? It may or may not be exactly a third, depending on how we're able to break it up, but that's the general idea, okay? And what's the impact on data path usage is that, well, now we can use all of these three pieces of the data path simultaneously, right? So before we were outputting data and then we were, executing something in the ALU, but whatever was happening up here was really no longer relevant, right? I mean, we were just kind of holding these same values even while those two values were computed and being brought back up into some register to save it back into, right? We were still just holding our initial input values. It's kind of pointless, right? Where we weren't utilizing that architecture. So now we're able to release registers, execute the ALU, and write back to the registers, all with three different pieces of data instructions. Okay, so let me pause there. Are there any questions? All right.
Would there be some delay due to all three processes having to wait for the ALU to transition down for the next clock cycle to begin?
Say that one more time.
I'm assuming that the ALU is on this one. So when the other two have to wait to transition until the ALU finishes?
So, I mean, in this example, we kind of have this hypothetical, we don't really have real numbers on it, So yeah, in theory, I mean, I can see the argument the ALU is going to take a little bit longer, but if that's the case, then essentially whatever your longest stage is, that's going to be your cycle length. So it may very well be, that basically, I, output some data from up here and it makes it to the input latch, right? And let's say 5 nanoseconds. Well, in the same 5 nanoseconds, you make the point, it very well could be that that data has only made it that far through the ALU. Well, if that's the case, then whatever it takes, right? Let's say that ends up being 10 nanoseconds and this was 5. Then what that essentially means is we're just going to sit here and let this data sit there for 5 nanoseconds. It's going to be pounding at the door, just waiting, let me in. As soon as the ALU makes it to here, which maybe that's 10 nanoseconds, at that point, we would hit our clock cycle and all of those gates would open up. Is that kind of what you're getting at?
Yeah.
Is that, yes, one of those stages might be longer. And if that's the case, then all the other data, even though it's ready and it could technically move on, it has to wait on that longest stage to compute before they all move on to the next one.
So in that case, when's the total, assuming that the other bus takes a time of 5 nanoseconds, when it be 30 nanoseconds instead of 20 for the entire, for it to get to its destination? Well,
if that was the case, then yes, we would have to say, well, this is now a 10 nanosecond, right? And this is a 10 nanosecond. So if you're just looking at one piece of data, then yes, it's going to take 10 to go through that first stage, 10 to go through the second stage, and then 10 to go through the third stage. Now, what a good designer might do is they might say, hey, stages 1 and 3 only take 5 nanoseconds. So this ALU shifter stage, it takes 10. Is there a way I can break this down into 2 separate 5 nanosecond stages? Now, that may or may not be possible depending on what exactly is going on. That would be the idea, is to try to get those so your goal is to try to get the stages as even as possible and to try to get them as short as possible, right? So you don't really want to have that case where we just have data sitting around waiting. May or may not be the only option. But in reality, by design, it typically, I think it ends up being a really small amount. I don't think it's as much as we're seeing. 50% of the time, you might have stuff waiting. Yeah, that's a great question. Any other questions? All right, good, thank you. Okay, so let's look at an example now. We kind of have broken down micro instructions on a non-pipeline example. So let's actually look at the swap micro instructions. Okay, so if we look at swap, you can see that we have 6 micro instructions. Okay, so what we're going to do is we're going to examine the code, see what it does, And in order to do that, I like to draw a table. So we're kind of going to walk through that. We're going to draw a table. And in this table, each of the columns are going to be the different registers and or memory locations that we kind of see pop up. Okay. And then each row are going to be essentially the result after a certain microinstruction. So how does each microinstruction impact certain registers? How do they change because of the instruction that was just executed? Okay. Memory locations, I kind of said the different registers. The memory locations, in this case, are going to be the stack top and the next to the top. Okay. Because remember, swap, what it does is it just looks at the stack and the operand stack, it takes those top two items and it's just going to swap them. That's kind of the idea behind a swap instruction. Okay. So if we kind of think about it that way, right? Let's just assume that this is what our memory looked like initially. All right, so I've got 6 items on my operand stack. You can see at the very top, I have a 9 and an 8. So my overall goal is to have this be the result, right? Or I've just swapped those top 2 values. So it's an 8 and 9 instead of a 9 and 8. Okay, so if I look at this, okay, if I start, so what I want you to do, actually, let's just look at init, okay? Look at init, grab a partner or two, and I want you to just try and figure out what would that top row have. Okay, what if we can't possibly know what the value would be in one of these registers and memory locations, we'll put a question mark or I'll just put a dash for now. Okay, but if we can reasonably know what should be in one of these registers and or memory addresses, let's fill it in initially. Okay, given, you know, kind of this initial memory location over here. So take about a minute, 30 seconds to a minute, and see if you can come up with the answers to that first row. All right. Which of these do you guys feel like good about? Yeah, like I can tell you the value for one of these at least. So someone shout out what they're like pretty sure about. Okay, so stack pointer should have what? 5. All right, now I don't know, my finger might be too fat to do this, but you know, I'll do my best. I was actually better than I thought I would do. All right, so 5. Okay, what else? MAR should be 4. So what makes you say that? So sorry. This is initially before we've run a single instruction. You're right, but you just ran after the first instruction. So I'll call on you after that. Okay, so top of stack would be not 5, but what's it pointing to? 9, right? So assuming that this the previous instruction set up things right, top of stack should be 9. Okay. And then what about memory 5? 9. And what about memory 4? Okay. And what about MAR and MDR? We don't really know, right? And same for H, right? Who knows? Okay. So I'll just kind of leave them dash. Now, I would normally fill out each one of these every row, even if it's a repeating, just because it's really hard for me to write into these boxes. I'm just going to only do it if it changes. Okay. All right. So after 1, John, what's going to happen? So we have MAR equals SP minus 1.
So SP minus 1
Okay. So basically we now know that, you know, we're looking at SP, and SP had 5. So we're going to have 4. Okay. Try to keep it in the box. Okay. And then what else? Does anything else change, or is any from the row before? Not really, right? Nothing that we can see. We did do a read command. Okay. So, but we're going to assume that the result of the read comes back the next cycle. At the end of the next cycle, then we can get that result back. Okay. So let's now look at swap 2, MAR equals SP. So what's going to change as a result of the next, after 2 row? SP, not quite. So MAR equals 5, right? Because we know that's basically what's happening. We're just copying whatever SP was, which is a 5. Okay, and then what's the other thing that's happening? The read's returning, and where does it return the value? Into MDR. Okay, so what value is going to be in MDR? It's going to be 8, right? Because all it's doing, right, is it's looking at saying, all right, well, I did a read on whatever's in MAR, which was address 4. So I look at address 4, and that, you know, was holding an 8. So an 8 is going to come back into that MDR. Okay, so we basically get that change now. All right, so now let's look at swap 3. H equals MDR, and then I do a write. Okay, so H equals MDR. So what's the obvious thing that's going to change here? H is going to be what? An 8, right? And anything else? We did a write, but do I get the result of the write? No. Okay, maybe at the next one. So let's look at swap 4 now. Okay, swap 4, MDR equals TOS. So what's the obvious thing? MDR is 9. Okay. It actually erases it. I think it figures out if you messed up. Okay. And what else happens here in 4? The write finishes. So what was the result of that, right? What was the result of that write? What did the write do? When the write command was issued, it was in swap 3, right? So it basically took the MAR and the MDR, current value of that, right? And what it should do is it should have written 8 at address 5. Y'all feel good about that? Agree with that? Okay. So what that means, right, is over here, memory 5, after 4, right, we should have an 8 in there. Okay. Anything else change this cycle? I think not, right? Because we just had, only thing that changed this cycle was the MDR, because it was literally overwritten, and then that write came back. Okay. All right, so now swap 5. Okay, so we're up here. All right, so MAR should now equal what? 4. Okay. And anything else right now? No, but we just did this right, so we got to keep that in our memory for the next instruction. Okay. Okay, so let's do that part first. So that write is taking the value of the MAR, which is 4. We just updated it, right? So it is going to write something at address 4. okay? And what it's going to write is whatever's in MDR, which is 9. Oops. Okay, so essentially we get a 9 down there, okay? And then finally, the obvious thing, right? TOS equals H. So TOS is now going to be 8. Okay. So if we look at this, right, we'll go 4, kind of bring those down, 5, 8, 9, 9, I'm sorry. Eight. Okay. So, right, if we kind of look, our main objective was instead of to have a 9 and an 8, to have an 8 and a 9. And we see that happen, right? We had a 9 and an 8, and now we have an 8 and a 9. And the other thing we just need to keep a tab on is the stack pointer. The stack pointer should still be pointing at the same place, number 5, and we see that that's true, right? So that's good. And then the last thing, or it doesn't really matter where the MAR, the MDR, and the H are at this point, right? Because we were using those and now we're done with them. But we need to make sure that we leave that top of stack register set up correctly for whoever has the next variable, because we assume that that was correct for us, right? We actually took advantage of the fact that the TOS register was set up properly. And so we need to make sure that the top of stack does indeed have 8, which is our new top of stack, and it does. So, so we successfully completed that in 6 instructions. Okay, so just as a reminder, this slide is not pipelining. This is just kind of showing us how we would walk through these micro instructions, the microcode instructions. Okay, so I just want to make this clear before we start to look at pipelining, because you'll see we're gonna break. I know it's hard to believe. We thought that assembly would be the lowest, and then we found no, there's micro instructions. And unfortunately, you thought that that would be the lowest. But what we'll see is these micro instructions are going to break down into micro steps. Are you following me? Okay, so assembly breaks down into micro instructions, and micro instructions break down into micro steps. Okay, so what's an assembly instruction? It's just kind of like a high level, a move, an add. What's a micro instruction? Those are the consecutive data path configurations that you need to realize that assembly language. What's a micro step? Those are what we'll see is those are the consecutive pipeline. It's like breaking down those control signals into just like smaller pieces for smaller pieces of the pipeline. Okay, so here's the final result, which I think doesn't match up. If you look at our bottom row, 4, 5, 8, 9, 8, 8, 9, 4, 5, 8, 9, 8, 8, 9. All right, so this code, we just kind of broke down non-pipeline, but this code is pipelineable, okay? So now in this next slide, we're going to take that same swap, okay? And we are going to break it down into micro steps, okay? Now, what I want you to do is before I even explain anything, I want you to look at this first. Let's just look at the chart. Okay, here's kind of a reminder of what our architecture looks like. I know it's small, but it's just to kind of remind you, hey, this is what we're working with. Okay, we have the A and the B latch here. We have the C latch here, and then we have whatever the register is here. Okay, so you can see each column here is a separate instruction. So basically, we're showing what's happening at each instruction. Okay, or we're showing. Let me say this again. Let me do it by the rows first. Each row is a different cycle, okay? And each column is showing where certain parts of that instruction are executed and when certain parts of that are executed in time. So what I want you to do is take a minute or two without any other explanation and see if you can kind of reason how this micro instruction, mar equals SP minus 1, and then a read, is broken down into these micro steps. See if you can make sense of this terminology. So take a minute or two and just talk that out with a few partners. That was for extra challenge.
Silly salmon. That's not true.
We just be having B equals.
Yeah.
All right, so I kind of heard some discussion. I think some of you guys are kind of getting the idea here. Okay, so with this swap one, let's just look at swap one. So remember, we're now talking a pipeline pipeline design. We kind of broke it down 3 stages. Okay, so the first stage is just getting that register SP into one of these latches, A or B. Okay, you could put A or B, although I think this ALU worked in such a way that if you wanted to subtract 1 from it, it had to be in the B latch. I don't really care so much about that, but getting that concept that, hey, yes, I just need my input register into these latches, one of these latches. Okay, so then the next step for that data right now that it's in the B latch is to cause it to flow through the execution unit. So that's why we see, flow through the execution unit and into that C latch. So that's why we see C equals B minus 1, right? So it's flowing through there and we're doing the minus 1, right? Obviously, if we kind of think of this like math equations where we could substitute variables, right? We just said B equals SP. Okay, so if we replace B here for SP, you'll see we have C equals SP minus 1, right? Which should kind of keep to the original instruction. Okay, and then obviously, right, the ultimate goal is to get that result into the MAR. So I say MAR equals C. Okay, so again, if you replace these, well, MAR equals C, well, C equals B minus 1, right? And then B equals SP. You would get here, if you keep doing those replacements, MAR equals SP minus 1, which is exactly what we started off with. It's just we did it in 3 steps. Okay, once we have MAR, once we have that value in the MAR, we can issue that read command. Okay, and then it's only in the next cycle where we actually get that whatever that memory, we go out to memory, and whatever was in that memory, it comes back into that MDR. Okay, and we'll say it's ready there at the end of the next cycle. Okay, so that's kind of how we would break down this simple instruction. Okay, now let's go to we just examined swap 1. Let's go to swap 2. Okay, so what are the micro steps of swap 2? Okay, so let me give you another minute or two and see if you can just come up with the micro steps. Don't worry about where they're going to be here, but what are the micro steps to basically carry out this operation right here? So see if you can write them down, and then we'll put them up there. So this one's a little bit more simple, right? we've got B equals SP, right? And we got C equals B. We're just gonna, all we're doing, right, is we're taking a value and we're just causing it to flow through the ALU untouched back into a different register, right? So we've got B equals SP, C equals B, right? So whatever came in on the B, I'm just gonna pass it to C. And then finally MAR equals C, right? So whatever's in C, I'm gonna pass it up in here to the MAR register, okay? But the next question is, when can swap 2 start? Okay, so take another 30 seconds. What cycle can we start swap 2? Can we start it right at 2, or do we need to wait? So think about that for a second. Okay. So in this one, we can actually start it in the next cycle. Okay, so obviously we can never start, at least given this microarchitecture, we can never start swap 2 in the same cycle because we can't be outputting, you know, 2 different instructions onto the bus, to the ALU. But if we look here, we have, you know, B equals SP, not a problem, right? Our B resources being not doubly used. Then we have C equals B, right? You can see it's a different microstep. And then a MAR equals C right here. And this would be a little bit of an issue, right? If, you know, in some sense, right, we can't write MAR at the same time. So the fact that it's in the very next instruction is good. Okay. So this one's kind of a vanilla, it kind of works as we would expect it, that best case scenario. If we go back to our graph that we started with, I'll go way back. Okay, to this one right here, where we just say, hey, cool, like next cycle, I'm gonna start a new instruction. That's the ideal, okay? But the reality is we can't always do that. Okay, so let's look, for example, the next one. When can swaps 3 start? Okay, and you can kind of see a little sneak peek there. 3 cannot start until cycle 5. Okay, why is that? Take 30 seconds. I mean, I kind of have the writing down here, but look at it and see if you can reason it through on your own. Why does swap 3 have to start this late? Why can't it start right here? Okay, so if you kind of look at this, right, we're in this swap 3, right? It's taking MDR, right? Which is the result of what? It's the result of the read from here, right? So, you know, we did the read here, and the result of that, remember, it comes back at the end of cycle 4, okay? So for that reason, we can't assume that it's there and accessible until cycle 5. Okay, so it comes back, and it's, you know, it could be fairly early on in the cycle that we get that result back, but we can't assume that it's there anytime other than at the very end of that cycle. So for that reason, even though we have MDR equals mem here, we can't read MDR into B at this point. So we wait till that next cycle, and then we can do something with it. And then from there, right, we can go on, right? B equals MDR, C equals B, H equals C, right? To kind of enable that H equals MDR. And then, right, we do a write. Okay, so the write, we execute that command, and then, we say again at the end of the next cycle, we have that MDR is into the memory, is written successfully into the memory. Okay, so we call this a true dependence, or you'll see all kinds of different terms for it: raw, read after write dependence, hazard or haja, if you will. These are all the same things.
Why can't write run at the same time and run on cycle 4 so that both memory and MDR goes at MDR?
Which you're talking about this right here?
Yeah.
Why can't this run where?
Cycle 4.
Cycle 4. Let's see. So the write is writing whatever's an MDR. So you couldn't do the write until the MDR, the value of MDR was set, right? Because that's what you're writing. So the earliest you could do the write was cycle 5.
Okay.
And you can maybe do that. I'm just kind of following the standard, right? Like, I mean, if you wanted to rearrange your hardware such that, hey, I can do writes kind of earlier. This hardware is just kind of set up so writes always the last thing. Reads or writes are the last thing it will execute. But from a data perspective, I think you're on to the right track and saying, yeah, I could technically do this. And this is getting to the idea where we looked at the no operation and we said, hey, let's just move this up here because there's nothing going on. So that type of thing is where you could start to get some savings. But you're at this point, you're starting to get into some maybe specialized hardware and you have to say, well, is it worth it or not? And that's a much harder question. Okay, and so then finally swap 4. I don't really have any issues here. I can just do the 3 steps. B equals TOS, C equals B, and then MDR equals C. Okay, so you can see MDR is just sitting there for a while. I was writing MDR to memory, but that doesn't matter. It's still staying the same. Okay, and then swap 5, same thing, no real issue there. B equals SP, C equals B minus 1, mar equals C. I issue that write command. Okay, and then at the end of the next cycle, whatever I had in MDR is going to be put into memory successfully. Okay, and then finally swap 6. Okay, so we really just had that one particular data dependency there. We call that a read after write dependency, right? Because I'm trying to read the data in MDR after it is being written into that MDR register. Okay, and I had that dependency there. Okay. So if we kind of compare these two, if we kind of go back to this one, right? We said, well, it took us 6 cycles to go through this, right? 6 of our micro instructions. Okay. And let's just say that, roughly these 6 instructions were 3, the length of our 3 micro, like the length of our micro step, right? Because we had this, let's just say we had we were running this whole, these micro instructions in 30 nanoseconds. And then we broke it down into 3 10 nanosecond pipeline stages, right? So if you kind of think about it like that, right? Well, 3 times 30, 180 nanoseconds versus down here with pipeline, again, each one of these is just 10 nanoseconds. You can see we had 11 of them. So 110 nanoseconds, if we wanted to think about it that way. So what we see, right, is with pipeline, we were able to actually save 7 microsteps, which is pretty significant, right? If you do just kind of a percentage, 6 out of 18 would be 33% reduction, right? So we have over a 33% reduction in our time. Okay, so that's the idea. let me pause there. Are there any questions on this design?
For swap one, did we want to write MDR equals map because of the read, the line above it?
Yeah.
And
Yeah.
say the right proportional.
Yeah, so it's just kind of implicit when you do a read command in this microarchitecture. What that means is, hey, you're going to read and eventually that result's going to come back and you're going to find it in the MDR at the end of the next stage. And likewise for a writes, then, hey, whatever's in the MDR, I'm writing that out to memory. So that's kind of why we have that syntax. Okay, any other questions on this kind of notation? Okay. All right, so this is just another way to look at it. Okay, this is like kind of a, this would be like a 4-stage pipeline. Okay, so each row is kind of showing a micro instruction. Okay, so this is instruction 1, instruction 2, instruction 3, and each column is showing the micro step. Okay, so instruction 1, if you just look at this one, right, it's gonna first do the IFU. So we kind of broke down these 3 in our data path, but we're going to add one before it where we're just fetching that instruction, okay, which would be basically this stuff up here. So this would be step 1, then step 2 is this, right? And step 3 is through the ALU, and then step 4 is that write back stage. And that's what we see, right? For instruction 1, it's going to be in the IFU, and then it's going to go into that writing out to the AB bus, and then it's going to go through the ALU and the shifter, and then it's going to be written back into the registers. Okay, so these gray boxes are showing which hardware is being utilized for this particular instruction. Okay, and this is instruction 2. So you kind of get this pattern, right, where you see the IFU is all, it kind of goes in this diagonal pattern. And then obviously if we, well, if we ask the question, how long does it take for a single micro instruction? Okay, how many steps does it take, or how many cycles for a single micro instruction? What would the answer to that be? We just look at this one row, right? How many steps does it take? 4, right? So 4 cycles. Okay, and then how long before the next pipeline instruction finishes after that first one? How many cycles? This is the whole concept behind pipelining, right? Is just 1, right? So from there on out, it's going to take 4 cycles for that first one to finish, but then from there on out, right, you're pumping them out. So every cycle, you're going to have the next instruction finishing. Now that's ideal, right? We just showed that that's not always going to happen because of dependencies or hazards, if you will. Okay, and then 5 columns, 5 through infinity are going to be pretty much going to be the same thing, right? We just kind of keep on going with that. Okay, so we started off with the 3-stage pipeline. We just went through that detailed example. And then the last slide, we said, oh, let's just convert it to a 4-stage pipeline where the first stage is now the instruction fetch unit. Okay. And now finally where we're going to end is with a 7-stage pipeline. Okay, and this is just a little bit more realistic. Okay, so before I even explain this, let me just give you some time, because I want you to take a minute or two and just kind of just stare at this graph a little bit and maybe talk it through with a neighbor and just see if you can kind of make sense of it a little bit, see how this relates to, this picture that we've been looking at over and over and over. So I think you would serve yourself to take a minute and stare at it before I kind of start to explain it. Okay, so if we look at this, we look at this graph. This down here is the main thing we've been looking at, right? We have registers, they go out to the AB bus, the ALU goes to the C bus, and the C bus writes back to the registers, and here's our to and from memory. Okay. This right here is the control store, right? That block that we talked about being in the top right for control store. This is the instruction fetch unit, which if you recall in the last slide was kind of hanging off over here, right? If we go back a few, it was a thing that was right up onto this side. Okay, so now let's kind of talk about these 7 stages. Okay, so stage 1 is the IFU, and this is what's going to fetch the next assembly instruction. You want to think about it like that. Okay, so it's going to fetch that assembly instruction. And then stage 2 is kind of decoding that assembly instruction into, basically it's figuring out the place in the control store where you're going to find those micro instructions. Okay, so don't worry so much. There's some details on here that I don't really care for you to know these finer details. It's talking about IJVM length and micro op ROM index. This is the main thing to see here is that, hey, this instruction here, this assembly instruction, for the most part, what it is it's just some kind of pointer to which one of these, lines, which one of these addresses in the control store is the address or the instruction we care about, right? So if we're doing an add, it's going to point to this chunk of micro instructions, right? If it's a load, it's going to point to this chunk. And then the length is just basically saying how many micro instructions is it long? Is it 3? Is it 6? Is it whatever, right? So there it is. I just explained it anyway, even though I said I wasn't going to. So that's that decoding step, okay? So, and just to be clear, this isn't decoding in the sense that we've been talking about it, that Medusa of wires, okay? That's actually going to happen down here. So in some sense, there's multiple decoding stages happening, but we're gonna call this the decoding stage, all right? And then step 3, what it's doing is it's taking this ROM, so remember ROM is just read-only memory, okay? This is just all those micro instructions. If you remember from slides ago, we had like 5 pages of micro instructions, for every possible assembly instruction that we could run. Okay, so this stage, all it does is it basically says, all right, well, you told me you wanted add, and there are 3 instructions, right? 3 micro instructions in add. So it goes ahead and copies them into a queue, and that's what this is. So queue, what is queue? In terms of in and out? FIFO, right? First in, first out. So the reason we have a queue here is so we can kind of decouple and make this a pipeline, all right? So maybe I have here in my, like I'm gonna do an add and then a subtract. So the idea is, hey, I'm gonna do an add, so I go ahead and I copy this to the queue, right? And then when the next instruction comes in, it can go ahead and it can find, okay, now I'm doing subtract, and I'm gonna copy those down to the queue down here after the add. Well, I maybe haven't finished executing all of the add micro instructions, right? So that's where the queue comes in handy, is I can just keep piling things into the queue and start to pipeline this design where I can, hey, now let me decode the next one. I don't have to wait till all the add instructions are done before I start decoding that next instruction and kind of moving it to that pipeline. So that's 3. And you can see there's a lot, here of details here, but that's the gist of it. Okay. And then we have all these, this queue of micro instructions. And those micro instructions are basically going to get passed down into, we had a micro instruction register. Now we have 4 of them. Okay. So if you recall from way, way back, let's go way back, man. I think we can do this.
Way back.
Way back. Wow, way back. There we go. All right. This is the MER, right? This is where we started. Control store pumped out the micro instruction, and then that's where the Medusa came in, right? Everything was wired. You remember this is before a pipeline. So it was wiring the C bus, the A bus, the B bus, the ALU, all from a single instruction. So the concept now, I'm not going to make the same mistake here. Okay. Okay, the concept here is now, get my little pointer back up. Okay. That instruction is going to flow through each one of these. Okay, so you can see for the first one, that instruction, I'm really only going to grab the wires that are coming off of the A and the B bus, right? And that's going to drive those registers out into that stage 4. And then once that's done, I'm going to take that register and I'm just going to slide it down into the MAR2, where you can see there, it's going to only take the ALU signals and wire them and do the execution for that. And then once that's done, I'm going to slide that down into MAR3, where it's going to take only the C registers, right? So it can basically drive that result back into the register. And then finally here, the last stage would be if I want to do that memory read or write. And this is kind of getting to Barrett, what we were talking about earlier. Our pipeline just so happens to be that whenever, if I'm doing a read or write, it's just kind of hardware built in. So it's the very last thing that's done. So we'd have to change our hardware to do that optimization. Okay. So this is essentially what we have, right? In our 7 steps, we have a instruction fetch, decode, the queuing of the micro instructions, and then the 4 stages here, which would be kind of what we're talking about as those micro steps, where we get the operands out of the register, we do the execution, do the write back, and then the memory. Okay. And, you know, just real briefly, this just kind of talks about some of the, well, I won't go through those. I'll add those to a short, maybe video. Okay, so the last thing I want to say in the last minute here is